this video, I want to start talking about or address the topic of fixed axis rotation, which is something that we have alluded to as we've been going, but I want to talk a little bit more specific about a couple things related to this. So fixed axis rotation is basically when we're looking at a point rotating around an axis, and that axis itself is fixed in place, and we're just seeing pure rotation. So we're going to revisit our basic equation that looks at the relationship between moments or torques and angular acceleration. So we've seen this before, that the summation of moments is equal to the mass moment of inertia times angular acceleration alpha. And when we're talking about fixed axis rotation, a simple example would be just a wheel, and this wheel is rotating around an axis, and as that wheel rotates around the axis, we can look at any point on the wheel. So for example, I might pick a point at the top right here of my wheel and say, well, what's happening at that point? I should also note that at that point, or really any point in a fixed axis rotation, we can treat the motion of that particle as traveling along some small segment, which we've called S, or arc length S, and that all occurs over some change in time. And previously we've shown that this arc length S is equal to r theta. So as this particle moves across the arc length has some angle associated with it, theta. We'll call that we'll say that it has a constant radius of curvature r, and for pretty much any object and any fixed axis rotation, we would say that that small segment has that constant radius of curvature, and we can use that as an approximation to get some equations out of it for anything instantaneous. And this isn't even limited to fixed axis rotation. This is true about any curvilinear motion around a curved path. So we'll start with this S equals r theta equation, and then from there we can take derivatives on the way down and get velocity equals r omega and acceleration, at least in the tangential direction, equal to r alpha, where omega is defined as angular velocity, and alpha is defined as angular acceleration. So we have these representations of position in terms of arc position S, velocity V, and acceleration in the tangential direction at least, which look pretty straightforward, right? We're just taking our linear approximations and turning those into the angular components, which are theta, omega, and alpha, and everything looks pretty straightforward. However, one thing that we've addressed before is that as this particle travels along, it has not only an tangential acceleration, tangential direction acceleration, AT, but it also has a normal direction acceleration. And the normal direction really captures the change in the orientation of the velocity vector. So the fact that the velocity may be changing in magnitude, but also is changing in direction. So to take that into account, and as kind of an aside, we could take a vector derivative of velocity to get to acceleration, and what we get is something that looks like this: S dot theta dot. And remember that the dot notation indicates that it's a time derivative. So we're seeing a time derivative of our position along the arc, and the time derivative of our angle, change in angle. Position along the arc we can think of as the magnitude of our velocity vector, and theta dot is just angular velocity. Well, from right over here, we see a relationship between v, which is actually, again, since I've not written it as a vector, it's what I'm talking about is the magnitude of that vector of the velocity, is equal to r omega. So that rewritten in terms of omega is v over r, magnitude of the velocity vector over r. And if I plug this in for omega up here, then I get that the normal acceleration is equal to the magnitude of the velocity vector squared divided by r. Similarly, I can realize that the magnitude of the velocity vector, again, as I've written over here, is equal to r omega. So if I plug that in, I have r omega squared, and this can similarly then be written as r omega squared, because the r squared cancels with the r in the denominator, and I'm left with that. So over here, for my key equations, I'm going to make note that omega, or the normal acceleration, is equal to r omega squared. All right, so this doesn't necessarily have to only apply for circular objects rotating about an axis located at their center. I can take any arbitrary object and spin it or rotate it about an axis, so I can give it some rotation, alpha or omega or alpha applied to it as appropriate. And then I can look at any particle or any location on that rigid body, and if I can measure the distance between them, labeling that r, now I can calculate my velocity vector. I'll give a different color here. I can calculate my tangential acceleration, and I can calculate or express my normal acceleration. And all of those things are applicable to any location on this rigid body, as long as I can define its location relative to that axis of rotation. The other thing that we want to make note of is that we have some sample situations that we've looked at before, and that is uniform rotation, which when we talked about linear motion, we called this constantly accelerated or constant velocity motion. So this would be like a constant rotational velocity motion. And the result is that we can write a similar equation, but now rather than writing in terms of position x, we're going to write it in terms of angular position theta. Similarly, we have uniformly accelerated rotation, and from that we get a similar looking set of equations, but now written in terms of their angular counterparts. And finally, the last equation here. All written in terms of their angular components. So ultimately what we end up seeing is that these equations under constant velocity, constant angular velocity motion, and constant angular acceleration motion, the equations are exactly the same, but now we've substituted in the rotational counterparts for the linear components. All right, thank you.